Welcome to today's session. In this problem walkthrough, we will explore problem number 555, titled Split Concatenated Strings. We'll break the problem down step by step, discuss potential approaches, and analyze their efficiency. Let's dive in. In this problem, you are given an array of strings called words, where each string is made up of lowercase English letters. The task involves two main steps. First, concatenating all the strings in words in some order to form a single string. Then, from this concatenated string, you will pick one of the original strings and split it into two parts, a left part and a right part. Your goal is to rearrange the strings in words in such a way that the resulting string, formed by concatenating the right part, all the other strings, and the left part, is lexicographically the largest possible. The input is a list of strings, and the output is the lexicographically largest string that can be obtained by following this process. With this in mind, let's explore some examples to better understand the problem. For the first example, the input array is words equals ABC, XYZ. The possible permutations of the strings in words are ABC, XYZ, and XYZ, ABC. Let's analyze these permutations. Starting with ABC, XYZ, the concatenated string is ABCs. If we split it, the string ABC, the right part is BC, the middle is XYZ, and the left part is A. Rearranging these gives the result XYZ. If we split it, the string XYZ, we get the right part is YZ, the middle is ABC, and the left part is X, resulting in is ABX. Now, considering the second permutation, XYZ, ABC, the concatenated string is XYZABC. Splitting it XYZ results in the same string as ABX as before. However, when we split it, the string ABC in the permutation, XYZ, ABC, the right part becomes BC, the middle is XYZ, and the left part is A. Rearranging these parts produces the string XYZB. Comparing all the possible results from the splits and permutations, the lexicographically largest string is XYZB. This demonstrates how the ordering of strings in words, as well as the choice of split, play a crucial role in determining the output. Let's look at another example to reinforce this understanding. Here's another example with words equals A, Z. Since there are only two strings, the only possible permutation is A, Z. Concatenating these strings gives AZ. Splitting it, the string A yields the right part as A, the middle is Z, and the left part is an empty string, resulting in the string ZA. Similarly, splitting it, the string Z gives the right part as Z, the middle is A, and the left part is an empty string, which also results in ZA. Since there's only one permutation and both splits lead to the same result, the lexicographically largest string is ZA. As a final example, consider a slightly more complex case with three strings. In this last example, words equals B, ba, A. One possible permutation of the strings is B, ba, A. Concatenating these gives the string ba. If we split it, the string B, the right part is B, the middle is ba, and the left part is A, producing the string bob. Other splits and permutations, while possible, result in strings that are lexicographically smaller than bob. This makes bob the largest string for this input. To summarize, the constraints of the problem ensure manageable computation, with up to 50 strings and a total length of 10,000 characters across all strings. Special cases include inputs with just one string, where no rearrangement is possible, or inputs where all strings are identical, resulting in no lexicographical improvement. Additionally, the concept of lexicographical order is key, as it determines how we compare and prioritize strings in this problem. To begin, let's explore the brute force approach. The intuition here is straightforward. We generate all possible permutations of the strings in the given words array. For each permutation, we concatenate the strings in the specified order and evaluate both the original and reversed versions of each string to ensure we maximize the lexicographical order. This means we're systematically going through every possible arrangement to find the largest result. The steps involve generating all permutations, concatenating the strings, and comparing the outcomes. However, the computational complexity of this method is significant. Generating permutations alone has a factorial time complexity, O(n), and when you add the cost of concatenating and reversing strings for each permutation, the overall complexity becomes O(n). *n*k, where n is the number of strings and k is the average string length. While this approach is conceptually simple, it quickly becomes impractical for larger inputs due to the explosive growth of permutations. The brute force approach, while intuitive, comes with clear trade-offs. Its simplicity makes it appealing for small datasets, but it becomes entirely infeasible when the input size grows, especially when n exceeds 10. This is why we turn to a more optimized strategy, the greedy approach. The key insight here is that instead of exploring every permutation, we can treat each string in the words array as a potential starting point for the concatenation. For each starting string, we consider both its original and reversed versions, and then concatenate the remaining strings in a fixed order. By focusing on maximizing the lexicographical order from each starting point, we can efficiently determine the optimal result without generating all permutations. This process involves rotating the array to simulate different starting points, which allows us to explore the problem space in a much more controlled and efficient manner. Analyzing the complexity of the greedy approach highlights its efficiency. Iterating through the words array takes O, n, and for each string, computing the concatenation and comparing results has a cost of O, n asterisk k, where k is the average string length. This leads to an overall complexity of O, n squared asterisk k, a significant improvement over the factorial complexity of the brute force method. The trade-offs here are clear. The greedy approach avoids the inefficiency of permutations by leveraging the cyclic structure of the problem, focusing on maximizing the result via strategic rotations and reversals. While the implementation is slightly more complex than brute force, the scalability and performance gains make it a far better choice for larger inputs. This balance between efficiency and complexity is what makes the greedy approach so effective. Given these considerations, the optimized greedy approach is the preferred solution. Its efficiency lies in the realization that we can maximize lexicographical order by treating each string as a potential starting point and evaluating both its original and reversed forms. By avoiding the factorial growth of permutations and focusing instead on cyclically rotating the array, we drastically reduce computational overhead while still exploring all meaningful possibilities. This structured approach ensures that we achieve the optimal result efficiently. The breakthrough insight here is understanding that the problem's constraints allow us to simplify the exploration process, making it both computationally feasible and conceptually elegant. While the brute force method is a useful baseline for understanding, its inefficiency makes it unsuitable for larger inputs, whereas the greedy approach strikes the right balance between performance and simplicity. To summarize, there are a few critical observations that underpin the greedy approach. First, to maximize lexicographical order, we must consider both the original and reversed versions of each string. Second, the cyclic nature of the problem allows us to replace exhaustive permutations with a linear exploration of starting points. By rotating the array and concatenating in a greedy manner, we can efficiently achieve the optimal solution. Comparing the two approaches, the brute force method is easy to understand but computationally prohibitive for larger inputs due to its factorial complexity. In contrast, the greedy approach offers a scalable and efficient alternative, though it requires careful handling of rotations and reversals to ensure correctness. For these reasons, the greedy approach provides the best balance of clarity and performance, making it the ideal choice for solving this problem within the given constraints. In this problem, our goal is to generate the lexicographically largest string from the strings given in the words array. To achieve this, we need to explore all possible arrangements of the strings, including their reversed versions, so that we don't miss any potential optimal solution. A brute force approach will help us cover all these possibilities. The first step is to identify all permutations of the words array. If the array has n elements, this will result in n permutations. For each permutation, we will generate two versions of every string, the original and its reversed version. This ensures that all configurations, including both forward and reversed orientations of the strings, are explored thoroughly. Once we have all the permutations, the next step is to concatenate the strings for each permutation. For every permutation, we consider both the original and reversed versions of each string. For example, given a permutation like ABC, XYZ, we generate the concatenated strings ABXIS, ABXIX, BAXIS, and BASIX. After creating all these concatenated strings, we then compare them lexicographically. This allows us to identify the largest string among them. To keep track of the largest string encountered so far, we use a variable that updates whenever we find a string that is lexicographically larger than the current maximum. Finally, after processing all permutations and orientations, the stored maximum string will represent our result, and we return it. There are a few key insights that drive this approach. First, reversing each string before concatenation ensures that we consider all possible orientations, which is crucial because the reversed version of a string can significantly affect the lexicographical order of the concatenated result. Second, by generating all permutations, we leave no room for missed orderings, guaranteeing that every possible combination is examined. However, this brute force approach is computationally expensive, with a time complexity of n * 2 to the power of n. While it is not efficient for large input sizes, it ensures correctness for small inputs. In terms of data structures, the words array holds the input strings, a temporary list is used to store concatenated strings as we evaluate each permutation, and a result variable stores the lexicographically largest string found during the process. The algorithm relies on a few key operations and reasoning steps. First, generating permutations can be efficiently handled using a library function, such as Python's iter_tools.permutations. Reversing strings is straightforward using slicing, like s:\1 in Python. Lexicographical comparisons are performed using standard string comparison operators, which most programming languages support by default. Additionally, since this approach has exponential complexity, it is best suited for small arrays, where n is 10 or less. Several edge cases must also be considered. For instance, if there's only one string in the array, the result is simply that string or its reverse, depending on which is larger. When all strings are identical, the concatenated result remains the same regardless of the order. Empty strings should be handled carefully to prevent them from affecting the concatenation process. Finally, for strings with mixed uppercase and lowercase characters, we must ensure that comparisons respect lexicographical order, where uppercase letters are considered smaller than lowercase ones. Analyzing the complexity, the algorithm's time complexity is O(n) due to the permutation generation, and for each permutation, we consider 2 to the power of n orientations, resulting in an overall time complexity of O(n) * 2 to the power of n. Space complexity is also O(n), because we need to store all permutations and intermediate results. Let's walk through an example to see this in action. Suppose the input is words equals ABC, XYZ. We first generate permutations like ABC, XYZ, XYZ, ABC. For each permutation, we consider all possible concatenated versions. For ABC, XYZ, we generate ABXs, ABXIX, BAXs, and BASIX. Similarly, for XYZ, ABC, we generate ZYZABC, ZISCBA, ZIXABC, and ZIXCBA. Among all these, the lexicographically largest string is ZIXCBA. Thus, the output for this example is ZIXCBA. The provided solution addresses LeetCode problem number 555, split concatenated strings. The objective is to generate the lexicographically largest string by rearranging and reversing parts of the input strings. ### step-by-step explanation. Step 1 *. The algorithm begins by ensuring each string in the input list strs is replaced with its lexicographically largest form, either the original or its reverse. This transformation ensures that subsequent operations are performed on the most optimal version of the strings. Step 2 *. The next step is to iterate over each string in the list. For each string, we treat it as the pivot and separate it from the rest of the strings. The rest variable contains the concatenated version of all strings except the current pivot. Step 3 *. For every pivot string, both its original version and its reversed version are considered. This ensures that no potential arrangement is overlooked in the search for the lexicographically largest string. Step 4 *. For each version of the pivot string, the algorithm explores all possible split points. At a given split point j, the string is divided into two parts, the part after the split and the part before the split. These two parts are rearranged, with the rest strings placed in between, to form a new candidate string. Step 5 *. The max function is used to continuously update the max_string variable, which holds the largest string found so far. By the end of the nested loops, max_string will contain the desired result. ### complexity analysis. Time complexity * the algorithm's complexity is O, n * m squared, where n is the number of strings and m is the average length of the strings. This is because for each string, we evaluate its original and reversed versions, and for each version, we explore all possible split points. Space complexity * the space complexity is O(1), as the algorithm operates in place without using additional data structures beyond the input and output. This implementation is optimized to handle the constraints of the problem and provides a robust solution to generate the lexicographically largest concatenated string. Here, we begin by defining the split-loop string method, which takes an array of strings as input. The goal is to determine the lexicographically largest string that can be formed by splitting and reordering the strings. First, we initialize a variable max string to keep track of the largest string we find. In the first step, we iterate through the input array and replace each string with its lexicographically largest form, either the original string or its reversed version. This ensures that we are working with the most optimal versions of the strings from the outset. Next, we start another loop to process each string in the array one by one. For the current string, we separate it from the rest of the array and concatenate the other strings together into a string builder called rest. This prepares us to explore all possible split combinations of the current string in the next step. For each string, we consider both the original and reversed versions to ensure we evaluate all possible configurations. Using a nested loop, we iterate through every possible split point within the current version of the string. At each split point, we create a new candidate string by rearranging the current string, taking the substring from the split point to the end, appending the concatenated rest, and then appending the substring from the start of the current string up to the split point. This forms a reordered version of the strings. We then compare this candidate string with the current max string, updating max string if the candidate string is lexicographically larger. Finally, after evaluating all strings and their possible splits, we return the max string, which represents the largest string that can be formed using the given input. To solve this problem, the first step is to transform each string in the input array into its lexicographically largest form. For the string ABC, we reverse it to get CBA, then compare ABC and CBA to determine the largest. In this case, CBA is larger, so we keep it. Similarly, for XYZ, reversing it gives ZYX, and we find that ZYX is the larger form. After this step, the updated array becomes CBA, ZYX. Next, we iterate through each string in the updated array. For the first iteration, we treat CBA as the target string and the rest of the array as ZYX. Now, we consider both orientations of CBA, which are CBA and its reverse, ABC. For CBA, we generate possible concatenations by splitting it at different positions. For example, splitting at position 0 gives CBA plus ZYX, resulting in BASIX. Splitting at position 1 gives BA plus ZYX plus C, which results in BASIX. Similarly, splitting at position 2 gives a plus ZYX plus CB, forming ASIX. We repeat this process for the reverse orientation, ABC, and calculate the possible concatenations like ABSIX, BASIXA, and ZIXAB. Among all these, the current maximum string is BASIX. In the second iteration, we now treat ZYX as the target string and CBA as the rest. We again consider both orientations of ZYX, which are ZYX and its reverse, XYZ. For ZYX, splitting at position 0 results in ZYX plus CBA, forming ZXBA. Splitting at position 1 gives YX plus CBA plus Z, resulting in XBA. Splitting at position 2 gives X plus CBA plus ZY, forming ECBA. For the reverse orientation, XYZ, we perform similar splits. Splitting at position 0 gives XYZ plus CBA, resulting in ZXBA. Splitting at position 1 gives YZ plus CBA plus X, forming ISCBAX. Splitting at position 2 gives Z plus CBA plus XY, resulting in SPAXY. Among all these possibilities, the final maximum string is ZXBA. This becomes our final output for this example. In the second example, the input array is the BBC. The first step remains the same, we transform each string into its lexicographically largest form. For a, reversing it still gives a, so the largest form is a. For BB, reversing it also results in BB, so the largest form is BB. Finally, for C, reversing it gives C, so the largest form is C. The updated array remains a BB, C. Now, we iterate through each string. In the first iteration, we treat A as the target string and the rest of the array as BBC. Since A and its reverse are identical, we only consider one orientation. Splitting at position 0 and concatenating gives a plus BBC, resulting in ABC. Since there's only one possible split for A, the current maximum string is ABC. In the second iteration, we use BB as the target string and AC as the rest. Considering both orientations of BB, which are identical, we calculate possible splits. Splitting at position 0 gives BB plus AC, resulting in BAC. Splitting at position 1 gives B plus AC plus B, which forms BAC. Among these, the current maximum string is BAC. In the third and final iteration, we treat C as the target string and AB as the rest. Since C and its reverse are the same, we calculate the split at position 0, which gives C plus AB, resulting in CAB. This becomes the final maximum string for this example. Therefore, the output for this input is CAB. Here, we begin analyzing the time complexity of the solution, which is broken into three main steps. First, we need to find the lexicographically largest form for each string in the input list. For each string, this involves comparing the original string with its reversed version. Reversing a string takes time proportional to its length, O, L, and since the total length of all strings combined is L, this step takes O, L, overall. Next, we iterate through each string to treat it as the split string, while concatenating the remaining strings together into a single rest string. Constructing this rest string requires combining all strings except the current one, which takes O, L, for each of the n strings. This makes the total cost of this step O, n asterisk L. These two steps set up the groundwork for the final phase of the algorithm. Now, the third step involves evaluating all possible splits for the current string. For each string, we consider both its original and reversed versions. For each version, we explore all possible splits of the string, meaning we divide it at every possible index. For a string of length L_I, creating a candidate string involves slicing the split string, concatenating it with the rest, and comparing it to the current maximum string. These operations, slicing, concatenating, and comparing, take a combined time of O, L_I plus L, for each split. Since there are L_I splits per version, and two versions to consider, the total cost for one string becomes O, L_I_2 plus L_I*L. Summing this across all strings results in O, sigma, L_I2 plus L squared. In the worst case scenario, when strings are roughly equal in length, this simplifies to O, L squared. Combining all three steps, the overall time complexity is dominated by the cost of handling splits, which is O, L squared, in the worst case. Next, we evaluate the space complexity. First, the input array itself requires O, L, space, where L is the total length of all strings. Additionally, during execution, the algorithm creates temporary strings, such as reversed versions of strings, the rest string, and candidate strings being evaluated. These temporary strings also require space proportional to their lengths, but since the total length of all strings is L, the maximum additional space required at any given moment is O, L. Finally, the output string, which is the lexicographically largest concatenated string, also requires O, L, space. Together, this means the algorithm operates with a space complexity of O, L, as it uses only in-place modifications in temporary variables proportional to the input size. Finally, let's compare this approach to a brute force solution. A naive method would involve generating all possible cyclic permutations of all concatenated strings and comparing them. Since there are O, n, permutations for n strings, and each concatenated string has a length of O, L, this approach would have a prohibitive time complexity of O, n asterisk L. The optimized solution avoids this inefficiency by focusing only on the lexicographically largest form of each string, either original or reversed. It also systematically explores splits for just one string at a time, combining it with the fixed rest string. This reduces the problem to a manageable O, L squared, time complexity in the worst case, while the space complexity remains O, L. This optimization represents a significant improvement over brute force and is well suited to the problem constraints. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases is a frequent issue. For example, you might encounter empty input arrays, arrays with just one word, or even strings that are palindromes themselves. If these cases aren't handled explicitly, the program might crash or produce incorrect results. Another common error is not considering reversals of strings. Since palindromes are symmetric by nature, failing to include the reversed version of concatenated strings can lead to incomplete solutions. Efficiency is also a concern. Using unoptimized methods to generate all permutations of the array can result in exponential time complexity, which is impractical for larger input sizes. Finally, skipping hash map optimizations is another pitfall. Hash maps allow you to quickly store and retrieve words along with their reversed counterparts, which avoids redundant computations and improves performance significantly. Addressing these issues is critical for both correctness and efficiency. Additionally, it's important not to assume that all words in the input array are unique. Duplicate words can introduce subtle bugs if they aren't accounted for, potentially affecting the correctness of your solution. Beyond coding, this problem offers valuable interview insights. Recognizing patterns is key here. The problem often centers around string manipulation, symmetry, and properties of palindromes. Understanding how reversing strings simplifies the problem can be a major breakthrough. Optimization is another area interviewers focus on. While brute force might be acceptable for brainstorming, they will expect you to explore more efficient approaches, such as using hash maps or even tries. Communication is equally vital. Thoroughly discussing edge cases and demonstrating tests for your solution shows attention to detail and a methodical approach. Lastly, be prepared to discuss trade-offs. For instance, compare the extra space needed for a hash map versus the time saved by avoiding redundant calculations. These discussions highlight your understanding of algorithmic design. This problem is also closely related to other challenges on LeetCode that you might find helpful to explore. For instance, problems like longest palindromic substring, number 5, palindrome pairs, number 336, palindrome partitioning, number 131, and shortest palindrome, number 214, all share common themes of string manipulation and palindrome properties. When it comes to alternative approaches, brute force is the simplest method. You generate all permutations of the array, concatenate the strings, and check each result for palindromes. However, this approach quickly becomes inefficient due to its factorial time complexity. A more refined option is the hash map approach, where you store all words and their reversed versions in a hash map for quick lookups. While it requires additional memory, it drastically reduces the time complexity. For more advanced scenarios, a tree-based approach can be employed. Tries are excellent for efficiently searching palindromic combinations, especially in larger datasets, but they come with increased implementation complexity. Each approach has its trade-offs, so choose based on the specific requirements of the problem. Great job making it to the end. In this session, we summarized the problem, discussed key takeaways, and emphasized the importance of efficiency analysis. Keep practicing, keep solving, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!